Good evening, everyone. So we will start with the session 8 for in the topic on nonlinear dynamics from basics to applications. Okay. Yeah, we will wait for 1 or 2 minutes. Yeah, hi there. So am I audible? Hello, am I audible? Okay. Oh, okay. Yeah, it's fine, it's fine. It's fine. So I will be sharing the videos, so you can any broken point you can catch, or you can just we can talk in the next session also. It's fine. Yeah, it's fine. Yeah, I messaged in the group. Usually, if she attends, she used to messages in that. Okay, so we will begin. So I will share the videos so that it will not be an issue for all of us. Okay, so I will start the session. Okay, so good evening. So welcome to the session on nonlinear dynamics from basics to application. So this is session 8. So in the previous session 7, I have just showed you some of the basic methods how to plot different diagrams or how to plot a vector field, and so you can check on those things, and I have attached the MATLAB code also in the file. You can try out them, and if any problems or issues we can talk in the next tutorial. Yeah, so in today's session we will complete the topics on bifurcations. So we have talked about closed orbits and all. So we will this session we will complete this session theory on closed orbits. We will see how circular orbits, how they emerge and how they turn on and turn off. So these kind of theories we will discuss today, and we will just slowly enter into the part called chaos and what is chaos and a simple example of chaos. So these are the major brief things which we will discuss in this session. And so these are some of the books you can refer to, and these are some of the reference videos. Yeah, so we will begin with the session 8. So I will just shift to the screen. Okay. Oh, okay. Yeah, sure. Okay. Hmm. Sure. Okay, okay. You can just tell me. We will stop at that. Okay, sure. Okay. Okay. So till the last session, we have seen that fixed points. Say the fixed points is was our focus, and we were seeing that fixed points were created, and some as you change the parameter, they were destroyed, and how they emerge, how they become stabilized and destabilization, how they happened, is what our concern was mostly. Now we are going to see how the oscillations, we were saying different methods to rule out closed orbits and all. Now our interest is to see how the oscillations, how they are created or how they are formed, and how they are destabilized and they are damped out. So these are the things of interest for us now in this scenario. So in fixed points, when we were learning, we learned about three different kind of bifurcations. We learned about saddle node bifurcation, transcritical bifurcation we learned, and we learned about pitchfork bifurcation. So this way our focus at that time was on 1D case, so we were seeing how the fixed points evolve and all. Now if we have a saddle node bifurcation, if we take initially, and say the equation initially it was x dot is equal to r plus x square or r minus x square can be written. So now what we consider is, say we have x dot is equal to, say, some other variable nu minus x square we have, and we have an additional 2D condition which is y dot is equal to minus y. Now if you have these two equations, so qualitatively if you observe, there will not be any much change in the x direction, only when you plot the y axis plots. So you will, when you are plotting the phase plane, you have x on this side and y on this side. Now if you observe the second equation, it's nothing but dy by dt is equal to y. So this is an exponential, e some a naught to the power e to the power y, e to the power t something it goes. Okay, if I write it properly, it is nothing but dy by dt equal to dt. Now if you integrate it, it's ln of y is equal to t plus c. Now if you take an antilog, y is nothing but e to the power t plus c sometimes y naught. So it's an exponential decaying, and we saw that it is minus y, so you will get a minus et. So any point that starts on this y axis will eventually try to decay down instead of going up, so it will try to come down, is what that exponential term indicates. Whereas the x-axis point, that is x dot is equal to nu minus x square, if you try to find the fixed points of it, this is nothing but equal to 0 you put, and x equal to plus or minus under root mu you will get. Now if you see what are the fixed points for this 2D case, that is x star comma y star, what are they? If you see, one case is plus root 2 comma 0, and the other case is minus root mu comma 0. So these are the two fixed points which you are having at your hand, and we know that x, if your y is equal to 0 condition is met there, then eventually your x also, x equal to 0 is also a fixed point when you are considering a 2D. So this we discussed in the starting case, because every time the matrix x dot is equal to ax matrix is always having the fixed point of 0 comma 0. So you have these fixed points in your hand. Now in these conditions, if you are looking into this, so say I have the fixed, these are two fixed points which I am saying we have. Now with this set of equations, we need to find for this 2D case how the trajectories evolve, or in the phase plane how the system evolves to, when we want to see when the new value are changing from greater than 0, when nu is equal to 0 condition and nu is less than 0. So we are going in this way, from positive to negative when we are going, how the system evolves is what our focus is, and we need to know how this system approaches to different fixed points. So when okay, so I will not write everything here. So when you are having nu greater than 0, you have x dot is equal to nu minus x square and y dot is equal to minus y. So you can find the Jacobian of this, and you can say for a given fixed point at root nu comma 0 and minus root nu comma 0, you can find the fixed points. So at plus root 2 comma 0, you will have a stable node. So this is found from the trace and determinant of the matrix. Since our major concern is not the how we are getting it, that's why I am not deriving that whole thing. And the other condition you will get is for saddle node is what you will get. So that means if you are plotting that, so you have two fixed points, say here and here. So this is nothing but root nu comma 0, and this is nothing but minus root nu comma 0. If you have, you see that this is a stable fixed point, stable node. So that means any point that starts anywhere will try to eventually come to this point. Similarly, anything down also will try to reach this point. Whereas this is a saddle node, minus root nu comma 0 is a saddle node. So anything that comes there, it will try to come towards it, and the other direction will try to move away from it. So anything starts like this will try to move like this, it will try to move out like this. This was the condition when nu was greater than 0. Now when nu is equal to 0 condition, so x dot is equal to minus x square, it's a general simple equation, it becomes 2. Then you have x equal to 0 comma 0 as your only solution. In that case, when you are plotting x comma y, so you will see that any point that starts over here will try to come like this, anything will try to come like this, because this side it's positive. So you will get a half stable node here, and anyone that is here will try to move away. So eventually your fixed point, this was a stable fixed point, it come and it coalesces into a half stable node. And now when you are bringing your parameter to next part, so since now it's a half stable node, and when you are increasing the parameter further, you will see that your system now doesn't have any fixed points, but still there remains a effect or influence of this fixed point for certain time when your value is very close to 0, but it is still less than 0, but it's still, if it is very close, you will see that there is some very small decay in large time it takes for the perturbation to die down. So what happens is it will take a long time for it to go to this particular infinite condition, and people refer this as the ghost state. It's called the ghost state because it had some influence previously, but still it feels that there is some fixed point was still present there, so it delays the perturbation from decaying very fast, so it will make it pass through very slowly. And so this kind of ghost effect, they say in terminology, that was the term that people used to say. Now our interest is to see how these fixed points, or qualitatively how you can explain these different things in 2 dimensions. We were interested all in 1D fixed points and all. So but in 2D case also, studying the fixed points itself will reveal lot of things in the 2D systems also. So 2D systems analysis also, understanding the fixed points evolving and emerging and disappearance, we can interpret lot of things. So for this current case itself, if you plot the null clines, that is x dot is equal to 0, y dot is equal to 0, I'll call the null clines which we had talked about. So say you have a null cline of like this, and you have a null cline which passes through like this. Say this was your stable node and this was our unstable node, and so this was our x dot is equal to 0 and this was our y dot equal to 0 condition. So in this null cline condition, null clines, the point where these null clines meet are the fixed points. Now if you observe, this was the case when you had 2 fixed points, that was nu greater than 0 condition. Now as you increase your nu, this x dot is equal to 0 becomes a tangent to this. That is nu equal to 0 condition, where a stable fixed point comes, and after that this moves up. So by studying this fixed point, by studying the point where your null lines meet, is enough for you to understand how the fixed points appear or disappear within a given range of parameter value change. So whatever we studied in one dimensional conditions, that find a fixed point and see how it emerges out and all, is very useful even for a two-dimensional system also. So that's the takeaway which we need to consider from here. And so this was the case for a saddle node bifurcation. Similarly, for any transcritical pitchfork bifurcations also, the similar laws apply to there also. You just need to find the null lines or x dot fixed points of that and see how they evolve, and you can interpret their evolution in the 2D plane. 2D cases also you can interpret them similarly. Now we are going to enter into a topic called half bifurcation. So this is the case where closed orbits are all coming into play. So suppose we had a two-dimensional system. Which has a stable fixed point. So when we had a stable fixed point, we know that the eigenvalues needs to be negative. That means the lambda 1 and lambda 2 values which you are getting from solving a given characteristic equation, they needs to be negative. If your eigenvalues are negative, they will be eventually decaying to a particular point. So that's why we need it as a stable node, or for having a stable fixed point, you need your eigenvalues needs to be, if they are real, and they need to be negative for you to get into a particular state, in a steady state, if I clearly say. So if I plot the real value of lambda versus the imaginary part of lambda, for a real fixed point, you will observe that your fixed points are lying on this x negative side of the x-axis. At the same time, when we say that we have a stable fixed point, there are two possibilities. One is either you can have the eigenvalues both real and negative you can have. So this was the case of that. You have real and negative eigenvalues. Apart from this, we can have one more case where you have imaginary eigenvalues. There also your fixed points, they lie on the, since if you have a complex eigenvalue, you will have a conjugate of that also in the system. So that's why they will be symmetric. Imaginary, yes, it's of the form, say a equal to small a plus ib form you will be having. A will be a real part. Based on the omega, you will be having a stable fixed point or stable oscillation state you will be having. Now when you are having a complex eigenvalues, you will be having both a conjugate of that also. Say if it is a, you will have a bar, which is nothing but a minus ai. You will have a complex conjugate of that also. Now in a physical system, when you are saying this, you have a complex number, what it actually means is, based on your term b value, you can say if it decays or is grows up. So if your imaginary part is negative, we will say that your oscillations, they try to settle down, and say you had a oscillation like this. If you had negative b value, then it will eventually decay down to a particular like this. Whereas there are certain cases where you had initially low, but then eventually the system will grow on to these kind of oscillations. So based on these things, there are these half bifurcation models are derived. So in half bifurcation also, so I will give a definition of what the half bifurcation means soon. there are two different kinds as we had in pitchfork bifurcation. We have something called supercritical half bifurcation. We have subcritical half bifurcation. Now, in a supercritical pitchfork bifurcation and subcritical pitchfork bifurcation, the only difference which we saw was there was a stable node and it bifurcated there in supercritical, whereas in subcritical you had only a stable here, then remaining was unstable. So you had a very high jump discontinuity at this point, then the system goes to very infinite conditions. So this was for supercritical and this was for subcritical. Pitchfork condition I just mentioned. Now in half bifurcation also, since you are now dealing with complex eigenvalues, so in a supercritical half bifurcation, you have a fixed point and you have trajectories that try to eventually come to these fixed points. If you start from anywhere, it will try to come to this fixed point eventually. And when you change your parameters, say you are this was condition when nu is less than 0, and when nu was greater than 0, your system will eventually try to move out to a limit cycle. So from a fixed point, it eventually tries to go to a limit cycle oscillations, and any condition outside will try to come towards this limit cycle. So a half bifurcation is basically you have a fixed point or a stable operation condition. From there your system even gradually grows to a limit cycle oscillations. So this growth is what you call supercritical half bifurcation. So we will, if you want to prove how this supercritical pitchfork works, say we will take an example. Say we had equation r dot is equal to mu r minus r cube and theta dot is equal to omega plus b r square. So we have some r, and in theta terms we have the equation. Now if so, this corresponding to this we have already drawn for when your nu is less than 0 and nu greater than 0, what are the conditions. Now if you want to see how the eigenvalues behave during the bifurcation, so for that what we do is we just convert this to Cartesian coordinates. So xy coordinates we will try to coordinate, which by just parametric writing x equal to r cos theta, y equal to r sin theta if we write. So from the x dot, from this equation we can write x dot is nothing but r times r dot cos theta plus r times cos theta differentiation is you will get minus sin theta, but then one more theta is there, so it will be d theta by dt, that is nothing but theta dot. So you will be coming up with r dot cos theta minus r theta dot sin theta. Now from the equation 1 we know that r dot is nothing but mu r minus r cube cos theta minus r theta dot is nothing but omega plus b r square sin theta. Now if you take a r common, so you will be left with r cos theta minus r times omega plus b r square times sin theta, and this r cos theta and this r sin theta is nothing but x and y we know, so it is nothing but mu minus r square. R cos theta is x, at the same time omega plus b r square is r sin theta is nothing but y. And from the equation, say we wrote x is equal to r cos theta and y equal to r sin theta, then the standard result we know x square plus y square is nothing but r square. So in that case nu minus r square is nothing but x square plus y square, hence x minus omega plus b into x square plus y square times y. Now if we expand it, this is nothing but mu x minus x cube minus xy square minus omega by minus bx square by minus by. So if now for our these things we will write nu x and minus omega y, and remaining all are higher order terms, minus omega y minus bx square and by square, sorry, yeah. Now remaining all will be higher order terms, so we write as higher order times in x or y it can. Now similarly, so this was for x dot we wrote. Similarly for y dot also we can write omega x my plus mu y plus higher order terms. Now so we have a equation of this form. So our regular method will be to find the Jacobian of this. So if we have x dot y dot, so Jacobian is nothing but dou f by dou x, dou f by dou y, dou g by dou x, dou g by dou y. So in the for the given case, if we do this, it's nothing but mu minus omega and mu. So we have eigenvalues for this of the form mu plus or minus I omega. So here the eigenvalues, they are imaginary, and for this to become stable to unstable, or for this eigenvalues to, it is currently in a stable state. Now for them to move to an unstable state, for this is you need to change the parameter from negative to positive. Then only your system will be crossing this. So it's like these imaginary points which we have shown now, they need to cross this to go to the unstable condition. And important thing to notice, the imaginary values of this eigenvalue. So in the half bifurcation, the limit cycle which we are all seeing now, because we have r cube and all, it's not actually a cylinder, circular, it's elliptical in shape, and this shape becomes distorted as the value of nu moves away from the bifurcation point. As nu moves away from bifurcation point, the shape gets more distorted. So, and one more important thing is, in our ideal case, the eigenvalues move on horizontal lines is what we were expecting. It will be moving like this. But the imaginary values of eigenvalue is strictly, it is independent of the parameter nu. So the eigenvalues, they not travel as we are expecting. They will not be moving in this way. Instead, since they are having a curve, they will be having a slope, and it will be trying to move, because it is a function of mu. Lambda eigenvalue is only a function of mu. So this is a conjugate of it. See, so this is real and imaginary. So they will be having a curved path, not as a straight line. They will not be passing on. They will be going on through a curved path. So they will cross the imaginary axis through a curved path is what we need to count. So they will not have any non-zero slope. They will have a non-zero slope. They will not have a zero slope, which we mean straight line. So that's one thing, how oscillations, they were initially stable. They can, for them to destabilize, they need to cross this imaginary axis for them to become destabilized. So this was the case for a supercritical bifurcation, half bifurcation. Now there is one more called the subcritical half bifurcation, and subcritical half bifurcations are more catastrophic. They are more dangerous, and in real life situations, they are, people need warning signals and all for these kind of sudden transitions, because subcritical gives you a very sudden change in their dynamics, and these kind of sudden changes most of the systems can handle that, and because they are not designed for such kind of oscillations. So people try to use different kinds of early warning signals and all. So I will try to give in tutorial 3 or somewhere, I will introduce you to different time series early warning signals what traditionally people use there, and how I will just show you how people have used these early warnings to show that there is some impending tipping coming. We will try 1 or 2 early warning signals, how they are behaving, we will see in the tutorial 3. So in a subcritical Hopf bifurcation, most of the dynamic people try to use these kind of early warning signals. And so the difference in equation, so in subcritical Hopf bifurcation, your initially it was minus, now it becomes plus r cube, and we take an additional term for stabilizing. So your oscillations can't grow completely, even it can't go exponentially to high limits. So we take a r to the power 5 to mimic the damping term. So minus r to the power 5 will reduce the oscillations to a particular value, and it will keep it within limits. And apart from this, we have omega plus br square. Yeah. So this remains nearly same. So for such a equation, now if you try to plot the phase space or in a r theta direction, if you try to plot, what happens in a subcritical Hopf bifurcation is you have a fixed point. Say we are talking all this for the case of nu less than 0. Trajectories which are close to that will try to come towards this fixed point, and you have an outer limit cycle also for this, but in between this you have an unstable limit cycle. So anything that starts will be thrown out, and it will be eventually coming to this fixed point, and anything outside this unstable limit cycle will be thrown out towards the bigger limit cycle oscillation that is present. What happens when you change the parameter, control parameter, is this unstable limit cycle, say earlier it was like this, this will now slowly shrink when your parameter is changing. It will slowly shrink down, shrink down, shrink down, and it will eventually it will engulf this fixed point. And finally what happens is, suddenly your system will see that it only has this bigger limit cycle only as a stable state. This becomes unstable, and suddenly the system sees only this kind of very high amplitude limit cycle as its only stable state. So suddenly from here to here, when your parameter here, when it became to 0, greater than 0, so at nu equal to 0 it remains, and it suddenly jumps to this very high amplitude oscillations. And so this is the characteristic of subcritical Hopf bifurcation. So if anyone in rude case, if you want to say is the bifurcation shown by the system, is it a supercritical, subcritical Hopf bifurcation, first thing we see is there any sudden change in the qualitative change in the dynamics of the system when your parameter is changing at a quasi-static manner or in a slow process. And the another property of subcritical Hopf bifurcation is hysteresis. That is, now if you change this parameter value nu greater than 0, so we expect that at nu equal to 0 this will again go back to this situation, but it doesn't happen. System takes a little more time, and it takes the parameter to reach nu equal to minus 1.4. So system it keeps these oscillations, it needs to build back this, it needs to bring back this unstable limit cycle, and it needs to have a fixed point here. For that it takes more parameter, you need to bring your parameter further lower down till nu equal to minus 1/4 for your system to come back to this starting state. So what happens is, you had like this, you had a state like this. Now this was your forward path. Now when you are coming back, you need to come back like this. You can't come the same path which you had come here. So this is not this thing, this is just a, so this is the reverse path. So this is your reverse path. and your system will come here and it will come down here. So from this region to this region, we call this as the bistable region. And so usually we refer this point where this starts as the half point of the system, and the point where it here it jumps down is called the fold point of the system. Should I stop now or? Okay. Yeah, so this was topic related to the subcritical and supercritical half bifurcations. Now, so these kind of oscillations, are they possible in real life? So we said that there are oscillations happening with these bifurcations, and are there any such kind of oscillations actually happening, or in real life situations are these kind of oscillations possible where you are having a stable limit cycle and then it suddenly jumps to unstable limit cycle oscillations and all. So I will show you one of the example which was found by a Russian chemist. His name is Boris Belosov. So it's famously called the BZ reaction, Belosov-Zebunovsky reaction. And what happens? Okay, so he used say 4 different types of chemicals in his reaction, and what he saw was there was a alternation in the color during the reaction, which was when it was carrying out, when his parameters were changing. We observed that the oscillation, the colors, which I will just show you the video how this behaves, and the colors, they started appearing, disappearing, they started changing their colors from red to blue, green, and they started having a periodically they start to shed these kind of different colors. And initially people never agreed to this, because chemical reactions, they believe equilibrium thermodynamics says all the things happens at a regular, they can't have this kind of non-linearities. But after in 1972, a biologist named Zebunovsky, he did the experiments and he showed that these kind of oscillations are possible in a chemical reaction. So it's in a chemical reaction he has shown it. So I will show you how the just it's a YouTube video, we can, for understanding, we can just see that, so that how oscillations are in, we need to know, because whatever we are learning, they all have a practical application, and this chemical reaction people have studied very widely, and they have seen these off bifurcations in all these models. So I'll just so he is explaining what happens. I believe you can't hear the audio, I think you can only, yeah, so I will just, so I have on the captions here. So he is BC reaction, he says. Titles are yes. So he says it's in 1958 some chemical reactions can oscillate. So this is how, so we had a uniform. When he stirred it, there was an unstable. Now the system has only one stable state where it needs to start doing these oscillations from blue to green to brown, not green, from blue to brown it goes, then it comes back to blue, and any particle of dust, it will eventually kick the, it gives a perturbation and eventually it goes back to this kind of oscillations. So when he stirred it, the system now has only one stable state. Sudden big limit cycle oscillation is what the system has. So these kind of oscillations are seen in real life systems, and this is one of the examples of these kind of half bifurcations what we discussed just now. And yeah, so that was one example. Now we will move on to the another topic, which is of, we'll just so we will mention this also here. So we discussed that there are these kind of half bifurcations which are possible. Apart from these half bifurcations, there are other certain bifurcations like this saddle node bifurcation and all, but people are not much interested in the 2D cases, that because these are very rare to happen and they need a very large the neighborhood. So half bifurcations, when we were mentioning, they were happening very close to the fixed points. They were near to the neighborhood of fixed points. Whereas now the saddle node bifurcations and transcritical bifurcations, they take a much larger plane, and so these kind of oscillation bifurcations, they are usually referred to as global bifurcations. Because these are not specifically restricted very close to the neighborhood of the fixed points which we have usually found. And so one of the example, if we take for a saddle node bifurcation, say we have equation of the form r dot equal to mu r plus r cube minus r to the power 5, and say one of them is like that, omega plus p r square. Now I will just directly plot the results and we will discuss on that, r and r dot if you are seeing. So initially when your mu is less than a critical value, you will see that your system had a single fixed point and all the trajectories will try to come to this particular fixed point. So in your r dot, so this was x dot, when we are plotting the vector fields we were saying that in r dot, if you see, you had a fixed point and any curve that is there, it will remains there, so it tries to move towards this fixed point. Whereas when your mu is now equal to the critical value, and if you plot the curve r dot, you will see that now this thing will slowly lift up and it will now be a tangent. So here what if you are seeing the fixed points, since this part is negative, your arrow goes towards this way, and this part is also negative, so this goes, so you will have a half stable here. So this means when you had a fixed point over here, curves will try to come towards it, and now you have a stable limit cycle that has emerged here. So anything that's outside here will try to come towards this limit cycle oscillation. Now when your mu is greater than the critical value, you have a fixed point, r dot if you plot, you have a fixed point and now it goes little bit higher and then comes down. So you have now 3 fixed points present here. and if you plot the arrows, this is this side, this is this side, this is this side. So now this becomes unstable, and here it becomes a stable fixed point. And if you draw the curve, you have a fixed point over here, and it tries to come towards this fixed point, and in between you have a unstable limit cycle and you have a stable limit cycle. That is the third fixed point that you have seen. So anything that tries here will try to come towards this curve, and anything moving towards this, it will move towards this fixed point. So now this, as you are changing the parameters from nu less than critical to the greater than critical, we see a saddle node bifurcation of cycles. So different cycles, they interact. Initially it was only having one, now it slowly interacts saddle node point it becomes, and it eventually have a limit cycle oscillation. Now that annihilation happens, and you will have an unstable limit cycle and a stable limit cycle. So they call this as saddle node bifurcation of cycles. Bifurcation of cycles. Eventually you are bringing down to a unstable limit cycle also. Now another kind of bifurcation people have studied is called infinite period bifurcation. So in an infinite period bifurcation, what happens is, this is somewhat like the ghost effect which we are saying. Eventually you had a fixed point, and when you are moving out of that fixed point, system feels that for a certain amount of parameter values, their system still feels that there is a fixed point, and the bifurcations take a lot of time for it to decay at that point. And when that happens, sometimes your time period that takes for you to decay any perturbation that you are giving there, it will take an infinite time to decay down. So that times the infinite, so that kind of bifurcation when you are exposed to, they are called infinite period bifurcations. For example, if you take, you had an equation of the form r dot is equal to r into 1 minus r square, and we have theta dot is equal to nu minus sin theta. Theta dot equal to nu minus sin theta, we have already seen. It's the nonlinear oscillator equation that we have just saw in the third lecture. And so if you are having this thing, so when, say, we will directly go to results, when nu was greater than 1, the system has a limit cycle oscillation, and when it's in the above phase, it is in the slow phase, whereas in the down it was at fast. So it tries to zip through this fast phase, and it takes a lot of time for it to cover this slow phase. And it had a unstable limit cycle in the center, so anything here, it will be thrown out of the towards this limit cycle oscillation when nu was greater than. When your nu is less than 1, when we reduced your parameter value, we observe that there emerges a fixed point in this, around this limit cycle. So there is an unstable fixed point, and there is a stable fixed point over here. So this unstable fixed point which was in the center, it is thrown out anyway. When it is thrown out, since this is a, now this and this are two paths where the system can go. Since this is a fix, so I will draw it with different colors so that we can, so this will be thrown out, and this thrown out can go in these two directions. Now the second point, this which is a saddle node point, so that means anything that goes here will try to go towards it, and other path it will be thrown out. Whereas this was a stable node, so anything that goes here will try to go towards it. So what happens is, if you start from here, this curve will be moving towards this, and it will go away from this, and this time period what it takes for it to go towards this fixed point, as t tends to infinity, the time period also tends to infinity. So it takes an infinite time for it to pass this slow phase now and move and come to a stable limit cycle oscillations. And these kind of things show scaling laws also. So they say that the nu minus nu c whole to the power minus 1 by 2. So minus 1 by 2 scaling also, or square root scaling also this show. And so that was one kind of bifurcation people have studied called infinite period bifurcations. And one more kind of bifurcation where people have studied more is called homoclinic bifurcation. So these are different bifurcations which involves these closed limit cycle oscillations, their stability and how they destabilize, and emergence of different unstable limit cycle oscillations. These are the different things, and for different scenarios how these are changing and what are the conditions. That's what we are discussing now. So in the homoclinic bifurcations, a part of a limit cycle moves closer and closer to a fixed point. So in short, if I say we have a x and y, if we have, and you have a saddle node over here, so anything that starts over here will try to move and say it is in this way it is. Now in a homoclinic bifurcation, any trajectory that starts over here, it will go like this, and say you had a limit cycle oscillation, limit cycle here, it will cover through this and it will move through it, and it will try to come back, and it will come towards this saddle. So this will take very long time for it to reach to this particular point, but this here it zips through very fast, but here it takes. So any point that starts over near to one fixed point and it takes a whole time period of time to come back towards that fixed point, these kind of bifurcations are called homoclinic bifurcations. And there is one more called heteroclinic bifurcations, where you start from some saddle node and you reach to some other saddle node point. So these, yeah, so and these two also shows scaling behavior. And so we will say, I will stop here. That's homoclinic bifurcations theory. We will move on. So these, I just wanted to introduce different bifurcations what people have studied, and we will go to another one more topic called the coupled oscillators. So till now we have discussed r theta coordinates, we have discussed different equations. So in a 2D itself, we can have, instead of, so we were discussing phase plane, and we discussed in cylindrical coordinates, r theta coordinates, how to draw the phase plane and all. There is in 2-dimensional one more thing, important 2-dimensional phase space is called the torus phase space. So this torus is nothing but it's like our vada, how it is, that's how it looks. So this is how it looks. So you have a torus is what we refer to. These kind of phase space are natural in some systems, and what happens is the general equation is of the form theta 1 dot is equal to some function of theta 1 comma theta 2, and theta 2 dot, say it's a function f2, is a function of theta 1 comma theta 2. So this is the general equation, and f1 and f2 are periodic in both arguments. They are periodic functions. And so if we write a simple example of this kind of equation, say we have theta 1 dot is equal to some omega 1 plus k1 sine theta 1 minus theta 2, and we have theta 2 dot is equal to omega 2 plus k2 times sine theta 1 minus theta 2. Now here theta 1 and theta 2, say you have a circle, theta 1 and theta 2 are the phases of the system. So this is theta 1 and this is theta 2. These are the phases of the system, and omega 1 and omega 2 are their natural frequencies. So this is like the firefly example which we have seen. Firefly flashes its light at a certain frequency omega, and its phase, the theta it started from which point in the circle is called the phase of the system. And here the k1 and k2, they are called the coupling constants. Now from this set of equations A1 we have, so this model was actually used to study the human circadian rhythms or the sleep wake cycle people have studied using. So this model was very famous for this sleep wake cycle understanding, and so people have more there's more theory in this, how to study the sleep wake cycle of humans and how much time and all these work. People were understanding more on these topics. So our interest here is, so we said that there is one theta 1 and theta 2 present in the system. Now to illustrate some generic features in a torus, features of flow on the torus. So what we do is, initially, say imagine there are two points which are running around a circle at an instantaneous rates of theta 1 dot and theta 2 dot. We had phases theta 1 and theta 2. Now they are running at a rate of theta 1 dot and theta 2 dot if they are moving. We could imagine that a single point tracing out of this trajectory, say you had theta 1 and theta 2. Now for you to say you have a bigger circle, and if you want to trace the path or a trajectory on a line diagram, if you want to say, how we will plot is, this is the theta 1 which we are considered, and this is the motion of theta 2. So what it explains is, by time theta 1 has gone one revolution, how much revolution the theta 2 has run. So based on this, so it's like a longitude latitude coordinates which we are now discussing. So that means you had two people running theta 1 and theta 2. Now to understand how much time, and it can, theta 1 can overtake theta 2 if it is speed is more. And for understanding that, we draw the diagram on a torus space. So how we draw is, we have theta 1 moving in this direction, in this direction it is moving. By that time, how much rotation the theta 2 has moved. Now if you plot that, you will see a torus like structure you will be able to say, you have this and you have this. So when you are moving in this direction, at the same time you are moving also in this direction. So if I put a color over here, it will be, so this is the torus thing. So this direction we are also moving, and this direction also we are moving. So this diagram, still people can understand that, but there were more sophisticated methods, and people, to understand it more, what they did was they made a square block with block diagram with, they say, square with periodic boundary conditions they created to understand this. So how it is useful is, since if you are going in the other side of this thing, so where I am drawing the dotted line, we cannot visualize that properly. So what they did was, they drew the 0 to 2 pi on both the x and y axis, and so the theta 1 and theta 2 they plotted. And now if you take any section over here, if it passes through this point, and if it's not, we can't see the other side of that. At that time, say it started from some point here, it moved through like this and it went out. Now this point is not after this, what happens is, it is actually moving in the other direction. But in the square plot, if you see, after some time this revolves and it may come from somewhere here and it goes in this direction. Now it moves like this and it may go like this, and somewhere it goes and it may emerge out from somewhere like this. So this is how in the torus phase space the actual trajectory is moving. And to visualize it more easily, people have used this square section. And so if any point that starts over here, say that was here, and it is moving like this, and it went to the other side, that means in this path it went like this, and now you have reached the edge. Now it covers the other rotation, it covers, and now it evolves, and when it starts to evolve, come back at this point, which I am showing by blue color. When it evolves from this point, you will see that it has, in the square plot, it comes out like this, and it moves out, and then when one more rotation it does, and when it comes back here once again, now by green, if I show here, so now this green path will come. So now you can visualize how many revolutions the system has taken, how many rotations it has taken. So people were more interested in this, and a simple case of that is when your coupling strength constants K1 and K2, when they are equal to 0, then your equations it reduces to simple linear oscillator model, which is nothing but omega theta 1 dot equal to omega 1, theta 2 dot equal to omega 2. This is by just substituting here K1 and K2 0, you will get that. Now the corresponding trajectories, they are now only just a simple straight line. That is, if you take d theta 1 by d theta 2, which is nothing but omega 1 by omega 2. So when you are drawing the phase portrait in a square diagram for this condition, you had, say, theta 1 over here, theta 2 over here. In these cases, when you are K1 and K2 are 0, you will have straight line trajectories. So they evolve from somewhere, and they cover back, and they come back. So what happens is, when this omega 1 by omega 2, say now these are in numerator by denominator form. If your P by Q is a rational number, then we can say that all the trajectories are closed orbits on the torus. That means they follow one circle, and they come back, and they go, and it goes like this. So it moves in this closed orbits, we can say. This is the condition when your P by Q is a rational number. That is, your frequencies omega 1 by omega 2, when they are showing rational number, you can claim this condition. So in this particular example, which I am say, this is the figure 1 which I have shown here. If you see, the P is 3 and Q is 2. So that means it has taken 3 revolutions of theta 1 by the time 2 revolutions of theta 2 has been done. Now this was the case when K1 is equal to K2 equal to 0 condition was there. Now an important or a major important theory which people came up with this was, what happens when your frequencies omega 1 by omega 2 is not rational, say it is irrational. Now that means P by Q is not equal to a correct integer value, it is now having some decimal points and all. Now in this case, they say the system exhibits quasi-periodicity. So we say the system exhibits a quasi-periodic behavior. So what quasi-periodic behavior means is, initially when you had a rational number, you had your straight line trajectories, and we said they are all closed orbits. When quasi-periodicity is exhibited, sorry. So if you draw the square diagram for quasi-periodic condition, you had 0, 2 pi and 2 pi you had. This is theta 1 and this is theta 2. So the systems will not have a closed orbit, and they will be moving very close to each of the trajectories. Say this was one trajectory. Now when it goes and when it comes back, it will never follow the closed path. Instead it will go very closely to this fixed point. Sorry, this trajectory. Similarly, if it starts somewhere here, if we say it goes very close to this trajectory, and it comes out like this. So these kind of behavior is shown. This is because if p by q was a rational number, you can see it crosses 2 times, it will go and then it will come back in the same path. But now since p by q is not rational, now trajectories will be very closely moving toward with each other, but they will not go in a closed orbit. They will not intersect by itself, and this eventually leads to a very dense torus on the structure. And what is okay, they said that they have discovered something like quasi-periodicity. This kind of quasi-periodicity is significant because it is a new type of long-term behavior. The system is not intersecting anywhere, but it is moving on, keeping on moving. It's becoming more dense and dense and dense. It's a new long-term behavior. Apart from, till now we saw fixed point, closed orbits, we saw homoclinic orbits, and now we have seen something called quasi-periodicity. And discovering a quasi-periodicity in your data or any of your processes is it's still a ongoing research, and people are showing that their system possesses quasi-periodicity and discovering this. So they say that for your quasi-periodicity to occur, your frequency should be having a incommensurate frequencies you should have. Then only its ratio will be irrational. So when you are having a simple time series data, say you are having a simple time series which you are getting from your any of the sensors or any of them, you can plot the frequency plot for them. So you usually take what is called the fast Fourier transform, and you plot the frequency FFT of that, and you will get dominant modes of the frequencies which is there. In that, the dominant modes, if they are incommensurate, this is the F1 and F2 are the omega 1 and omega 2 which we were discussing here. If they are incommensurate, that is their ratios are not in integer values, then or rational numbers, then we say that the system exhibits a quasi-periodicity behavior. And one important thing is, there are transitions from stable operation, they move through quasi-periodicity behavior, and then they go to this other periodic oscillations. So this is a intermediate state, and once you identify that these are intermediate states, the biggest advantage is now you can say if quasi-periodicity system is exhibiting, the next state will be undesired state for us. So it's like an early warning. If you are seeing quasi-periodicity, immediately you can sense that there is something going to be wrong. So that's like an early warning it is now becoming. So that's how people have seen to it, and lot of systems, from neural brain activities to lot of things, even in the in our rocket engines and gas turbine engines also, we see this quasi-periodicity behavior, and it's still a ongoing research, understanding the quasi-periodicity behavior in physical systems and how they are evolving. And in a transition, if you are getting, there are few limited examples where they show quasi-periodicity behavior in a system when your parameter is changing, and capturing them is quite difficult in experiments, but still there are experimental evidences which shows quasi-periodicity behavior also. So that was the case for we were discussing for quasi-periodicity. Now another important topic which we can talk of is called Poincare maps. So these Poincare maps are useful for studying swirling flows, such as the flow near a periodic orbit. Till now we were discussing everything on closed orbits and all. Now we are discussing on, so I will just write it down. They are useful for studying swirling flows such as flow near a periodic orbit. Now what we do in this thing is, say consider an n-dimensional system, that is, say you have x dot is equal to f of x, and and this is n-dimensional if we consider. Now we consider a surface S such that its dimension is n-1 dimensional it is. Say if you have a 3-dimensional system, then if it was 3, then this is 2. So this is a surface which we are considering. Now say you have a path like this, your path like this going, and your arrows are in this direction if you see. So this is a 3-dimensional we have in our hand now. Now if we take a surface S such that it is in the transverse path of the flow, that is, it is in perpendicular direction to the flow how it is going. If that such kind of S surface if we are able to build, and once this is built, what we focus on is, now if you see the surface separately here, you can see that one rotation of this curve, if it starts, say we started somewhere here, it goes like this, it goes, and now if it's a periodic cycle, it will pass through the same point again, and then it will go like this. That means if you in the surface, if you see, it is only just a one dot, and at the same time in the next circle if you see here, if it started somewhere here, it moves on like this, it moves and it moves like this. If it's a periodic closed orbit, it will move and it will go through this itself once again, back to back. So you will have one more circle, one more point there. So these are, say this is x star, this is x n+1 x star, and you will have a lot of points on this surface. So this is we should be careful that S is to be required to be on the transverse to the flow, that is, all trajectories starting on S should flow through it, not parallel to the surface. It should not be flowing parallel to this surface. Everything should be flowing past through this surface. Now the Poincare map P, say we refer P as the Poincare map, is a mapping from S to itself, obtained by following the trajectories from one intersection with S to the next. So I will just write it down. It's a mapping from S, that is our surface, to itself. So we started some point on S and we are looking where the trajectory comes back once again. That is the mapping from S to itself, obtained by following trajectories. By following trajectories means we are following that path that we are showing here from one intersection with S to the next. So if it's not a periodic orbit, what happens is, you started somewhere in the point here, and the next point, if it's not periodic, it will pass through somewhere here, and next point it will pass from somewhere here. Now using this Poincare map method, you can actually say your system is having a closed orbit, or it is having a random behavior, or what is it we can say. So if you had a random behavior in a Poincare map, if you see, you will have very random points all over the face. Now if you have a periodic oscillation, your point will be going, every point it will be going through that point itself back to back. Now how this is useful is to quantitatively show that your system is exhibiting a chaotic behavior or a periodic oscillation behavior. It's a standard method that we plot the Poincare section or Poincare map of this, and we show how that there is a single point emerging from here to here, there is a system transition happening. So this how quantitatively we prove, or we claim our evidence from the experiments or any of the model results which we get. We try to what we try to strongly say our claim that by using these kind of tools, and Poincare method and Poincare section is one of those tools which has been worldwide accepted. And if you are able to show these plots in the results which you have got, then people now in the community, they accept it, and they say they agree to that. Okay, you are showing a fixed point, you are showing a point in the Poincare section, then it will be a periodic oscillation state, and this, if it's random, you can say it's a chaotic behavior and all. So that's the importance of having a understanding why Poincare maps are required, and obtaining a Poincare section is very useful. Now, okay, if I will just finish it by a small example we will write, and we will stop the discussion on Poincare map on that. So say we have a polar coordinate equation r dot is equal to r into 1 minus r square and theta dot equal to 1. So it's simple equation we have. Now the surface S we consider be a positive x-axis, we have already told. Now if you want to compute the Poincare map for this, say we have a initial condition r naught, and say I am plotting here the graph. This is r value. Now the initial condition on S r naught we have taken, and we know that theta dot equal to 1 is already given in the equation. Then the first return of S, first return of a, not of 2S happens after a time of, so we say the time it takes is time of flight t is equal to 2 pi it takes. Then the r1, the next point will be nothing but the Poincare map of r naught. So then the r1, it should satisfy the condition that integral r naught to r1. So we know this is nothing but dr by dt equal to r into 1 minus r square. So now if we rearrange it, you can write it is as dr by r into 1 minus r square equal to integral 0 to 2 pi dt. This integral 0 to 2 pi dt is nothing but 2 pi, that is the time of flight it takes. So finally what you have is integral r0 to r1 dr by r into 1 minus r square should be equal to 2 pi. If this condition is met, then you can find the next point r1 where it is going to meet. So now if you take the integral of this and all, you will finally boil down to an equation of this form, minus 4 pi times r0 minus 2 minus 1 whole to the power minus half. And in short, so this is, and if you know r1 is nothing but we will just, so this was our r1, so that was 1 plus e to the power minus 4 pi times r0 minus 2 minus 1 whole to the power minus half. So in r1 was nothing but p of r naught. Now if you try to generalize this, p of r will be 1 plus e to the power minus 4 pi r to the power minus 2 minus 1 whole to the power minus half. So this is from this only. When you do r2, it r0 will become r1 and this left hand side will become r2. So we generalized it to this. Now if you plot the graph of this, so this p of r will be somewhat like this. This is your p of r and this was our r in the x-axis. Now we draw a straight line with 45 degrees like this. This is our reference line where theta equal to 45 degrees is what we consider here. So this I will discuss why we consider 45 degrees only for a line as this, because when we study 1D maps, one-dimensional maps, when we are studying, we will discuss thoroughly why we take this. So currently we will say that there is a line, reference line here, and we started somewhere here. So I will change the color. we started somewhere here R0. Now we proceeded with R0, and the next point of intersection here is, this is our R1, which is nothing but P of R0. Now if you want to see the next point of intersection, just move horizontally to this 45-degree line, then from there you move on to the next intersection. This will be your R2, P of R1, and you can similarly move in this form and you can get all the intersection points, and this will be your R1, this will be R2, and so on. So this diagram is what usually referred to as cobweb diagram. So this cobweb construction enables us to iterate the map graphically. Now you can graphically iterate the different intersection points you can get, and you can plot the different points in the intersection wherever you are getting. And so at this point, when your intersection was there, this is the case where R star was equal to 1. So this intersection point, what is the specialty is, this is the point where we had the stable and unique limit cycle oscillation. So that was the case where 45 degrees and the P of R intersect. That's the point. There is some specialty in that point, and in this case it was the case where we had stable and unique limit cycle. So this is the things which I wanted to discuss in the bifurcation theory. Okay, now it's already. So I will just move to the next thing which we will discuss, which topic called chaos. Basics. I will just, okay, since it's only half an hour, I will show you certain videos and how people have interpreted them and how they discovered chaos and all we will discuss. So when we are saying the term chaos, the first person who comes to who has talked about this was Lorentz, and we come to his equation called Lorentz equation. And so the Lorentz equation is a simple model. It is something like this: sigma minus yx, y dot is equal to rx minus y minus xz, and z dot is equal to xy minus bz. So if we look carefully, we have in this simple model we have only two non-linearities, xy and xz, and the remaining sigma, r, b, they are all parameters. We will discuss them in detail. So in Lorentz, he derived this three-dimensional system from a drastically simple model of convection rolls in the atmosphere. So it's like, so you have cold, say hot land, you have cold atmosphere above, so there are convection rolls that happens. So if you remember, there is something called hot plate, and then if you are sending air over it, you will have convection rolls. So this convection rolls he modeled using this simple three equations in the atmosphere. He was interested in weather forecasting and prediction, and these are also some equations which arise from models of lasers and dynamos also. After that, people have seen through it. So Lorentz discovered that this simple looking deterministic system, that is this, so we call this as the system, could have extremely different wide variety of behavior, and the solutions oscillate irregularly, never exactly repeating, but so they will never, okay, so what he said was, this system showed different dynamics and solutions oscillate irregularly, not a regular limit cycle oscillations or anything. it's a, we should be thinking that this is a deterministic system, which means you can predict the next step of that system. It's what deterministic system means. But he says that these kind of systems, they oscillate irregularly, never exactly repeating. Never exactly repeating, but always remaining in a bounded region. So it remained in a bounded region of phase space. So this was his thing, and people initially they didn't accept, but then eventually when it was discovered and it was able to say, now currently this never repeating case, this is what we people call it strange attractor. And so in order to understand what this chaotic behavior is and how system shows random behavior and all, so we need a simple deterministic system for that. So the example which we will consider here is a simple example called water wheel. So I will show you two different cases. One is based on a simple bucket used video or a simple setup where people show this water wheel experiment, and I will show one more video by the Strogatz himself where they have their own more sophisticated mechanism of showing this water wheel experiment. So we will see to both of this, and we will understand what is chaotic in this and how in experiments they have seen this. So I will share the screen once. Yeah. So the first video we will see is a simple video. So we have it here. So this is the water wheel experiment. So this is the experimental setup. So you have different buckets being kept at the different hands of this thing, and you have, so he shows that there is a small hole at the bottom of the each bucket, and they have a mechanism, pump mechanism for sending the water from the top. Now with the rate of how the water is flowing, based on that your system, this is a, it's like a wheel. Now this wheel rotation changes, and in a regular when your water flow rate is very small, system will not even start rotating, because you don't, your inertia is more dominant. For the bucket to rotate, it should at least fill half, then only that weight will try to make it rotate. Now when your flow rate is slightly high, when you are increasing the flow rate of liquid, you will see that the bucket will start rotating in one particular direction, and once it crosses a particular more value of a flow rate, we will see that now the system can rotate in either direction, and it can do different oscillations. It will not even complete certain one rotation, by before that it will come back. So this is what they claim as irregular dynamics. Now we will see how they, in practical, how they see it. So now they have this is the bucket they are showing, and now they are going to on the water. So they have on it. Now the water is coming, and now slowly the wheel started, and the first bucket slowly started filling, and it takes some time. Now it started rotating. Now the wheel is rotating in what particular direction, and we can see that the wheel is rotating in what particular direction. Now it has reversed its direction, but now if you see, it moves in one particular, now it stops, it doesn't complete that full complete rotation, but now it moves in the other direction. Now if you take a time series of this movement of the wheel, you will get a very irregular dynamics. We will show that in the Lorentz system how that behaves. And so one more interesting thing which we need to know here is, so now in this case they are showing 4 different cases. So they start the experiment by putting the flow rate at, say these are at different conditions, now they are putting. These are 4 different cases they have started. Now if you see the first one started rotating, but the third one has already started rotating. Now the first and second, they are slowly started rotating out. Now, so the takeaway from this scene, what I wanted you to take away is that it's very sensitive to the initial conditions. The point how the flow rate is coming, based on that the system whole dynamics is now changing. Now the third one is rotating in different way, whereas the first and second are moving in different ways. So the same setup we are using, but based on your initial conditions, the erratic dynamics shown by the system is completely irregular, and it's a deterministic system. Actually, you can tell if your water is filled in this way, it should move in this direction or this direction. You just need to solve the energy equations. You should compromise with the conservation of mass and energy. You will be able to say which point the system should go. But still, a slight change in the initial condition makes the dynamics move very differently. So this is one of the characteristics of chaos. It's very sensitive to the initial conditions. So this is one of the experiment. It's called the chaotic water wheel experiment. And so the next the video which I wanted to show is okay, so it's okay. So this is Stephen Strogatz himself, and they are describing the water wheel experiment. So this is the water wheel they have in MIT. So I will tell what are the different components of this system. So these are different columns of water here. If you can see the columns here, and over the top of it you have a manifold. In the black color you see a manifold. So they send the water. So in the water they put food color they are putting, so that we can see the water getting filled in this transparent columns. And in this manifold they have put different holes in the manifold, and only up to this region only water will be coming. So if your columns are within this region, they will start getting filled up. And this is lifted from the ground, and it's positioned in an inclined position based on this knob which I am showing by the arrow. So they can shift this. So the one control parameter they have is this knob, how much angle they need to tilt. And the other parameter which they have is, this is the brake which they are applying. It's like this rotation of this wheel can be fast or slow based on this brake which we are tightening or loosening here. So these are the two control parameters in their hand now. Now he shows initially. So now he ons the water now, and once the water is on, you can see a green color liquid getting filled up in the columns. So these are the different columns, and the water is getting filled from this manifold. It has sprays, small holes through which water is filling into this, and each column of this has a small hole at the bottom. That's why when it is getting filled, it goes down also, because it has a hole inside it. So each column has holes, and the water goes drip down from that end. Water drains down. So I will put CCT also. So now he keeps the brake at certain So the two parameters which I mentioned, one was the angle that determines the gravity effects, and the other brake determines the coefficient of friction, rotational friction. So he placed it at certain position, the brake, and now he started rotating it in one direction. And now from the manifold the water is getting filled, and you can see that the little green colored water is getting filled uniformly over the whole place. So the brake is at some mediate in between condition, and it is uniformly rotating. There is no special thing, but it's keeping rotating in one direction, and water is getting filled symmetrically. Now he turns it in the other direction also to check if that same behavior is seen, and he sees that the same behavior is seen. The system rotates in the other direction peacefully in the same way. Now he stops it, and now he changes the brake. He tightens the brake now. So now the friction is more. Now it takes more effort to turn in the wheel. Now he sends it. Now since the brake is very tight, the water gets filled, and once it's getting filled, now whichever part it is more filled, it tries to go that side, and it's rotating in one particular direction now. Now since the brake is very tight, the system moves in one particular direction only. So he says that the brake was too much tightened, that's why it's showing that behavior. It's not uniformly rotating because the liquid distribution is different. Now it has rotated in the other direction. So this is unpredictable. Now it goes in that other direction. So this irregular dynamics is what they were interested in, and now it goes in the other direction. So I will just hold on. We will see the complete video. It's only 1 more minute, so I think it was peaceful. So it goes, and it now so he loosens the brake now a little bit. Now it's little more free now, so it rotates completely, and it rotates more fastly now. Now it goes back in the opposite direction. Now it's completely random, it's completely irregular. It goes some time, and now it goes back. Yeah, so these are the two examples of showing the chaotic behavior in the Professor Strogat's textbook. So yeah, so it's 8:15, so we will just talk about one small topic, and we will stop for today. So in his textbook he derives the complete derivation of how this water wheel is happening and what are the different equations. So he derives equations similar to that of the Lorentz equation which we described initially. So we will not go into the derivation now. Important thing we need to do is, so the Lorentz equation or the water wheel experiment which we have seen, they have some non-linearities, or the terms which I mentioned here with red. These are the non-linear terms involved in this system. When we have these kind of non-linear nonlinearities in the equation, in a simple deterministic equation, the system shows very wide variety of different behavior. But an interesting thing to note is this Lorentz equation is symmetric in nature. Symmetric. So which means that if I put x, y, z as minus x, minus y and minus z, still the equations remain same. So it's symmetric in nature. And one more another important thing is Lorentz system is dissipative in nature. So by dissipative we mean is it loses its energy. So we have given a hole in the each column's bottom end. So there is a dissipative effect being shown there. By dissipative in a phase space, what we mean is the volumes in phase space contract under the flow. So we want to check if this equation, water wheel or the Lorentz equation which we have in our hand, for this dissipative system, is it the volume is decreasing or not? We will check it. So for that what he does is, so we should see how do volumes evolve. So in a phase space, how volumes evolve is our question. So in order to answer that, what they did is they took a three-dimensional equation, say x dot is equal to f of x, a general equation they took, and they picked a arbitrarily closed surface s of t. Say this is your s of t. It's an arbitrarily closed surface. It's an arbitrarily closed surface of volume v of t. Say you had a full volume v of t. Out of that, I am showing the front view of that surface. So s of t is the front view surface of that. And now we are considering a point on S as say it's the initial condition. Say we consider some point on this initial surface and any point on the surface, and we try to let them evolve in a time delta t. So you had a surface initial condition on the point on the surface S. So I will just write it down. Initial condition, we had a point. We had a point on S and we allow it to evolve for a dt time, small dt time we allow it to. Now, so the surface S evolves to new surface S of t plus dt. Then our question is, if it's a dissipative system, the volume should decrease. So what is the condition of v of t of dt is what our question is. So after dt time, your volume, say your surface now has gone to this condition. It is now S of t plus dt. So S of t plus dt it went. Now what happens to the volume? V of t it is there. V of t plus dt is what is it. So if you take a surface like this, the outward normal to the surface is n, and any velocity of, if you are having a trajectory, the velocity will be tangential to that. So that is say f. So here what n denotes is the outward normal and f denotes the instantaneous velocity. Now once clear with these two things, so f dot n is nothing but outward normal component of the velocity. Now when there, so we take a small slice of the surface, say you take a small slice like this and say that area is dA. Now with this velocity f n into dt, it covers a distance of this much Fn into dt distance it will cover. So this will be the new extra area which the system has gained. Now extra volume that it gained is, so say okay, we will write as Vt plus dt is nothing but the initial volume plus summation of volume swept out by any tiny patches, all the tiny patches like this. There are a lot of tiny patches in the total surface, like this hole is there. The sum of the all of these tiny patches volume increment is integrated over that will be the total volume, that is Vt plus dt. So actually Vt plus dt means what? It is nothing but V of t plus, so you can convert this volume integral using the, it can be converted. So it's for a one case, this is nothing but integral f of f dot n dt times dA over the surface for this small surface, and you integrate it over the total surface. This is for this one particular piece of the surface, into dA is the area. Like that you integrate it over the throughout the surface to get the extra volume that you have gained in this process. Now if you rearrange it, you can see that V it is nothing but Vt plus dt minus V of t, and if you take the dt to down here, you are left with here is S of f dot n dA. And if you remember the differential equation, what is derivative of a system, it is nothing but Vt plus dt minus V of t by dt. So this is nothing but V dot. So, and this is the surface integral. So we have two different theorems called Gauss divergence theorem and Green's theorem. From the divergence theorem, you can convert the surface integral to a volume integral. Because we are dealing everything here with volume, we need to convert this surface integral to a volume integral. So if you have f dot and dA, the volume integral of that will be converted as gradient of this f into dV. So that's the divergence theorem. So in our case, the del dot f for the Lorentz system, we had x dot is equal to sigma into y minus x, and y dot is nothing but rx minus y minus x, and z dot is equal to xy minus bz was our equation. And if we want to find the gradient of that, so it is nothing but dou by dou x of sigma into y minus x plus dou by dou y of rx minus y minus x, sorry it is xz, plus dou by dou z of xy minus bz. Now if we take the derivative of it, it is nothing but sigma times minus 1 plus dou by dou y of minus 1 plus dou by dou z of minus b. So you are left with minus sigma plus 1 plus b. This is the gradient of f. So this tells that the gradient of f is every time less than 0. Any, let sigma b be any value. So the volume rate v dot is equal to minus sigma plus 1 plus b. It is less than 0 every time. And so if you substitute it in this equation, that is v dot is equal to integral over v f dot and dv. This is nothing but minus sigma plus 1 plus b into dv. So v dot is nothing but minus sigma plus 1 plus b times v. So which has a solution. So v dot is equal to some constant, these are all constant, times v. This is nothing but an exponential thing, which is nothing but say some initial value v naught e to the power minus sigma plus 1 plus b times v. Okay, sorry, t it is. Yeah, so the volumes in the phase space, though this tells that the volume in the phase space exponentially decay. and exponentially decay, or so okay, when you are saying volume, we will not use the word decay, we will use the word called shrink. So the phase space shrinks exponentially fast. So if we started with a very large amount of big blob of things, or in some example they say that you have a balloon and you are sucking out the air in the balloon completely, so your volume slowly decreases down. So all the trajectories that are starting in the blob now end up to a very limited space. So it started somewhere like this, now they are very small a volume they are, so they say that this is near zero volume. So if you know something, we will discuss something called butterfly effect and all. So here the trajectory, they cover a zero volume, that means that width of this is very small, so the trajectories are moving so closely that the width of this total thing, if you sum it up, it's very close to zero. So that's what we call the zero volume condition. So your trajectories, they shrink down to a very low volume, zero volume, and so the volume contraction imposes strong constraints on the possible solutions of the Lorentz equation. So this Lorentz equation, so we have seen that, so our question was how do volumes evolve, and we have seen that volumes in the phase space, they exponentially shrink for a deterministic system like Lorentz equation. And so this constraint, that zero volume constraint is there, and your system can't intersect, trajectories can't intersect, and they have very zero volume. Now how will the system behave? So it should move like this in very fine manner, it should be doing some kind of different behavior, it should be exhibiting. And chaos is very random also, so it should be random, it should not intersect with each other, its volume should be nearly close to zero. So all these conditions should be met in the Lorentz equation, these are all met, and eventually the system goes to certain strange attractor, we say. So that's the main concept here. So our takeaway from this thing, what was that? It's our Lorentz system is a dissipative system, because volume shrinks when you are moving from a within dt, when you are changing, the volume exponentially decays, or shrinks, not decays. Yeah, so I think it's all 8:28. So this is the concept till now I have prepared. Yes. So so I think next Tuesday is fine, I think. No? Okay, yeah. Are there any questions or anything you wanted to? Okay. So last thing, it's MATLAB code only. I think I have shared the MATLAB code also. You can just run them. My aim was in the tutorial one was to show you how to plot the diagrams which we used using the p-plane and all. When we simply click, you are getting the figures and all. I wanted you to learn how to plot them. So I have showed the vector fields, how to plot a line over that figure, how to solve using Runge-Kutta fourth order method. So that was the main concept. So you can just try over it in MATLAB, and you yourself can plot it and feel how the trajectories evolve. It's how you feel, and different equations how they evolve is our main. So dynamic systems theory is completely based on this. So I wanted you to learn that. So that was the previous session. So you can just go through, and if any questions we can discuss in the next session. Yeah. So then, yeah. Okay. Okay. Yeah. So then, yeah. Good night then. Thank you.